How can a particle pass through a solid wall without having enough energy to go over it? Today, we will explore the strange quantum effect called quantum tunneling. We will first define the classical barrier problem and then explain how the wave nature of matter solves it. Classically, energy determines if an object can pass a potential barrier, like a tall hill. If a particle does not have enough kinetic energy to clear the top of the hill, it must stop and return. Energy conservation forbids the particle from suddenly appearing on the other side of that hill. However, in the quantum world, fundamental particles behave both as particles and as waves. This is the concept of wave-particle duality, where every electron has an associated wave nature. The particle's location is described by a probability wave, known as the wave function. When this quantum wave encounters a barrier, most of it reflects, matching the classical view. But because the barrier is not infinitely high, a small part of the wave function leaks into the wall. The Schrödinger equation shows that the probability wave exponentially decays inside the barrier region. If the barrier is extremely thin, the decaying wave does not reach zero before it emerges on the far side. This tiny, non-zero wave amplitude means there is a probability of finding the particle beyond the wall. This surprising penetration through the barrier, where the particle never truly enters the forbidden space, is tunneling. This tunneling probability is very sensitive to the width and height of the barrier. Let's consider a worked example of an electron tunneling through a thin insulating layer. If the barrier is only 1 nanometer wide, the electron has a measurable chance of tunneling through. If we increase the barrier width to 2 nanometers, the tunneling probability will drop extremely fast. This shows tunneling is a practical effect only over truly atomic distances. One real-world application is the scanning tunneling microscope, or STM. The STM tip uses quantum tunneling of electrons to generate incredibly detailed images of surfaces at the atomic level. Another crucial example is nuclear fusion inside the Sun. Protons lack enough energy to overcome electrical repulsion, but they tunnel through the barrier to fuse together. We learned that quantum tunneling allows particles to bypass energy barriers based on probability waves. This amazing phenomenon makes atomic imaging possible and powers the stars of our universe. Generate your own educational videos for free at eduvids.vercel.app.